Howdy Calc AB, welcome back. Thanks for tuning in for another video lesson today. Today we're going to kind of do the last little piece of curve sketching that is a standalone item before we start putting them all together into one sort of set of skills. And what we're looking at today are limits at infinity. And so we talked earlier about how a limit could approach infinity, or a function could approach a value that is infinite. That is, so as x approached c, we got positive or negative infinity. We called that unbounded originally when the function was unbounded. The limit doesn't exist. This is different. This is as x approaches infinity or negative infinity, what is the behavior of the function like? And so gonna flash back to some algebra 2 and some pre-calc days where you may have experienced finding horizontal asymptotes, and that's essentially what we're talking about here. So we're gonna have to break through one sort of misconception I think a lot of us have about asymptotes, and then we'll get into how we actually find these horizontal asymptotes in just a little bit. So first things first, when we talk about a limit as x approaches infinity, what we mean is that as x gets infinitely large, or infinitely small, the function value seems to be approaching a single value. And so what we think of in this case is kind of like a boundary or a bound on the function. And so, we've seen this in the rational functions when we did those in algebra 2. So let me start with one of those. If I have the old rational function, where we had, oops, that's a straight line tool, sorry. Where we had the function coming up like this, and it was approaching 0 as x got infinitely large, and then it had a behavior like this on the other side, and it approached 0 as x got infinitely small. We called that a horizontal asymptote. And that's really what we're talking about here, at least for the first part of today, is, what is the behavior as x approaches infinity for our function? Is it approaching a finite value L? Okay, or as we approach negative infinity of f of x, is that approaching a value? Let's call it k. And I'm gonna call those different letters, even though you're used to, from algebra 2 and pre-calc, the function, the rational function, always approaching the same value as you went to positive or negative infinity. That was because you're in pre-calculus you weren't quite ready for the possibility that it could approach a different value if you went to positive versus, say, negative infinity. And so prepare yourself, because that is going to happen. We are going to see some functions where we approach a different value as we go left to negative infinity versus we go right to positive infinity. The other thing I want to break down for you is somewhere along the line, you probably had an instructor tell you that an asymptote is like a boundary line, like a line you can't cross. And while I think a vertical asymptote, we can say with confidence that the vertical asymptote is that line. The horizontal asymptote, I'm sorry to report, is not that way. The horizontal asymptote actually can be crossed up to and exactly infinitely many times. Yeah, it's not a line that it can't cross. It could cross it over and over and over again. Okay, the horizontal asymptote, that's what these are. These are horizontal asymptotes. And that means we don't really care what happens, in near the origin. We don't, it could be crossing the x-axis, the horizontal asymptote infinitely many times. What we care about is that as x gets infinitely large, okay, is it approaching a value? Or as x gets infinitely small, is it approaching a finite value? And if it does, then we call that basically the horizontal asymptote for the function. And so my example for you for this one is is one that I think, well, we'll look at the graph of it here in a minute. But if I define f of x to be the sine of x divided by x, okay. Now we know what sine of x does. It's a nice wave function, right? Up and down, always between positive and -1. Okay, but what happens if we divide that function by x? Okay, first of all, okay, as we know, sine of x over x, as x approaches 0, you remember? Squeeze through. That's going to approach the value of 1. But what happens as x gets infinitely large? Okay, and so before I do the sine of x over x, let's think about a simpler function. What happens if, that's supposed to be a d, I don't know what happened there, if my function that I call d of x is some constant divided by x. Okay, as x gets infinitely large, this is a fraction. And in a fraction, if the denominator is getting bigger, right, what's happening to the fraction? It's getting smaller, right? So this approaches 0. Well, now sine of x isn't a constant, of course, but it's never bigger than 1. It's never smaller than -1. So it sort of makes sense, right? That the same idea, the limit as x approaches infinity for sine of x over x will also be 0. Okay, which is okay, great. But here's what I want to show you. It crosses the line, y equals 0 infinitely many times. Let's go over to Desmos and take a look. So let me bring in our graph here. And as you can see, exactly as I said, the maximum value is 1, clearly. And here's where sine of x over x bounces up and down over the x-axis many, many times. But as x gets infinitely large, it does approach 0. If I add the graph 1 over x, you can see how nicely that just follows it just down to 0. And if I add y equals -1 over x, you can see how from the underside it comes up, squeezing, if you will, that function in between. Exactly what we said. Y is approaching 0. It's just doing so on this graph from the top and the bottom, crossing infinitely many times, which is pretty cool. It sort of breaks down that one idea that you had before in your head that you can't cross an asymptote. Well, turns out, yes, you can. So let's head back to the whiteboard here and let's take a look at how we might find some of these horizontal asymptotes or limits at infinity, rather than do them graphically. Because as you know, we want to be able to do them graphically, numerically, analytically, and in words to make the College Board happy. So I'm going to start with a function here, and we're going to use that idea again that if we have x in the denominator, maybe we can come up with a way to use that to evaluate some of these limits. And so this one, limit is x approaches infinity of 2x minus 1 over x plus 1. And again, I'm looking for that horizontal asymptote for this function. Now, if you remember the rules from Algebra 2, okay, and you may not remember the rules from Algebra 2, and that's okay if you don't. I'll put the rules from Algebra 2 up here in a little bit. You probably already know what the horizontal asymptote for this is going to be. It's going to be 2. Okay, but let's take a look at how using calculus we would show you that the limit is 2 and why the rules from Algebra 2 work. So let's do that. So what I'm going to do is I'm going to say, well, all right, as x goes to infinity right now, I'm going to get 2 times infinity minus 1 over infinity. And infinity over infinity is sort of this indeterminate form. And so we might be like, well, I think I need to simplify this. And here's what we're going to do. We're going to multiply by 1. Just a very bizarre looking number 1, but there it is. And so by multiplying by 1 over x over 1 over x, look what happens to our limit here. We get 2 minus 1 over x over 1 minus 1 over x. Now, as x goes to infinity, what happens to the 1 over x terms, right? They go to 0, both of them. And we are left with our limit as x approaches infinity of 2 over 1, which of course is 2, just like we said. So there you go. And notice in this case, it does not matter if you go to negative infinity. 1 over x still goes to 0 as you go to negative infinity. So we still have 2 over 1. Even if I put a negative sign in there, it does not change what's happening here. And so we get a nice horizontal line at 2 that we approach from both sides. And we could take a quick look at that graph if you want, and then we'll come back to this and just take a peek at another example here. So let's go over to Desmos real quickly and see what we have. Here we are, and check it out, exactly like we said it would be at y equals 2. We have a nice horizontal line. In fact, we can just add that right on the graph, and you can see there that black line that we are approaching 2 from as we go to positive infinity and to negative infinity. So that's a nice algebra 2 example. I think one that we're pretty familiar with already. Okay, so I know I've made a kind of a big deal out of it, but what about the ones where we might go to a different value when we go to positive and negative infinity, right? Well, let me show you an example of that. And this kind of breeds an interesting phenomenon that happened a couple of years ago. Well, it's been a lot. I think a couple of years, 13 years ago, 14 years ago. I get it. Some of you weren't born. But on the AP exam, there was actually a problem that involved this, and it was on the multiple choice section, and they had to throw their multiple choice question out because so many of the kids who got 5s got this wrong, and in the scoring notes, of course, you know who's to blame, right? Yeah, calculus teachers. We didn't do a good enough job, apparently, of getting our students ready to consider the possibility that this limit, as x approaches positive infinity, compared to this limit, as x approaches negative infinity, of our function 3x minus 2 over radical 2x squared plus 1, could possibly result in 2 different horizontal asymptotes. Well, it does, and here's why. We're going to do the same kind of thing. We're gonna multiply by 1. This time though, the numerator, sure, 1 over x will work just fine. 1 over x works in the denominator as well, but I'm going to make it 1 over the square root of x squared. Okay, so that's still 1 over x, right? But that way I can bring it into the square root, and that's really what I want to do. So if I do that, limit as x approaches infinity, notice I'm going to get 3 minus 2 over x in the numerator. In the denominator, I'm going to bring the 1 over x squared into the radical. Well, that would just cancel out the x squared on the first term and would give me 1 over x squared on the next term. Okay, distributing in here. Okay, well, now as x approaches 0, what happens? I'm sorry, as x approaches infinity, what happens? This goes to 0. This goes to 0. Oh, why do I still have an x in there? Well, that wouldn't be there. It would have canceled out already. It's because the x squared really canceled. And notice I just get 3 divided by the square root of 2. 3 over root 2. Okay, no problem. Okay, piece of cake. But remember, I'm allowed to multiply by this blue term here, 1 over x over 1 over square root of x squared, because that's really 1. Right? Okay, now here's the situation. When I do the integral over, or the limit over here on the right, okay, I multiply 1 over x over 1 over the square root of x squared. As x is approaching negative infinity, that's not 1. Okay, because think about that. X is negative, right? Now, 1 over the square root of x squared, that's going to be a positive number, right? We talked about that in algebra 2, how when you do an even root, of an even power and you get an odd power, 1 over x to the first, you put absolute values on it, right? So that it's always positive. Called it the principal root sometimes. Okay, well, that means that's a positive in the denominator, but the numerator is a negative. So I'm actually multiplying by -1 right now in the pink. That's not right. You can't do that. So we have to put a negative sign up here on the numerator. And that is what changes so that we actually end up with 2 different horizontal asymptotes. Notice I'm going to get -3 plus 2 over x over the same thing in the denominator here. 2 plus 1 over x squared. Okay, that's supposed to be an x, and I did a poor job of writing it. So let me rewrite that. So that now as x goes to infinity, okay, this term here will go to 0. This term here will go to 0. And you see I get a limit of -3 over the square root of 2. And so the ones to watch out for have radicals in them. When you're finding the limit as you go to positive infinity, come back and look at the limit as you go to negative infinity, because they could be different. And I think it's worth taking a look at this graph on Desmos so that you can actually see it, because it is quite strange. All right, and I'll just bring it up over here. And as you can see, we definitely have some interesting behavior there, right? Notice I've put on the two horizontal asymptotes there. The red one is positive 3 over root 2. And you can see as we go to positive infinity, that's the line we approach. But notice on the negative side, as we're going out that way, look what happens. Yeah, we are approaching the negative one. That orange line is at -3 over the square root of 2. So yeah, could have 2 different horizontal asymptotes. And you never saw that before when you were in your pre-calc or algebra 2 classes, I don't think. So yeah, kind of a weird thing. But you got to watch out for it. And boy, College Board made a huge deal out of it one year, that's for sure. So anyway, wanted to highlight that for you. All right, I mentioned the rules for finding horizontal asymptotes that you learned in algebra 2, and those are still valid. They're not, it's not like we've just made those invalid. You can certainly do those. It's just that if you have to prove why you have that horizontal asymptote, you need to do it with calculus. So using the limit as x approaches infinity or x approaches negative infinity is going to be how we establish that. So let me just review those rules with you real quick though. So let's pop those on the screen here. All right, so these were the rules that you had algebra 2. We just had a weird power fluctuation or something go on in my house. So if there was a weird like in the video, yeah, that's because I had to edit it real quick there. Yeah, it was weird. All of a sudden my second monitor shut down and lights flickered and everything, but everything's back on now, so I don't know what that was. Anyway, so back in algebra 2, or maybe it was pre-calc, you know, it depended on who you had. If you had me for an algebra 2 teacher, we definitely would have done these rules. But I know they're not in our textbook, so sometimes they don't always make it into the class, especially with the coronavirus last year. But that wasn't any of you guys anyway. If your degree, so if you have your function f of x and it's of the form p of x over q of x. So in other words, you know, I didn't write it out there because it's hard to type math on this lame keyboard that they give me in Zoom. So basically p of x over q of x. So it looks like this. Look at the degree of the functions, right? So look at the degree of p of x, look at the degree of q of x. If the degree of p of x is less than the degree of q of x, then that's easy. Y equals 0. The x-axis is going to be the horizontal asymptote for the line, or for the graph of f of x. If the degrees are the same, then what you do is you take the ratio of the leading coefficients. We actually saw that early on, that very first one. I'm like, oh, hey, if you remember, you know, this is first degree polynomial up here, first degree down here, and notice what we ended up with was, yeah, the ratio of the leading coefficients. So that's a rule that we've seen before. The last one, if the degree of p of x is actually bigger than the degree of q of x, so the numerator has a bigger degree, then we don't have a horizontal asymptote. Okay, there isn't a horizontal asymptote. There is no limit as x approaches infinity. It's going to be infinite. It's unbounded. So you don't have to worry about it in that case. You still probably need to show it, right? So use your calculus to show that that limit is infinite. But we'll kind of know ahead of time what we're aiming for. And I find it's always easier if, like, you know where you're supposed to land. It makes the life a lot easier when you're trying to evaluate these limits. I did say though for number three, watch out, because if that degree of p of x is exactly one bigger than q of x, then you know you've got a slant asymptote, and you should find that. And if you don't remember how to find a slant asymptote, don't worry. We are going to review that, just not today. Today is about limits at infinity. And so um, we'll look a little more closely at how we find that slant asymptote down the road. There is a good example. I was just looking for it here. Example 8 in the textbook shows you how to find a slant asymptote. So if you are curious about how to find that slant asymptote, example 8 kind of shows you. It involves some polynomial division. So, all right, guys, that is limits at infinity. So thanks for watching. Thanks for hanging out. We'll be working on this in class. If you're in Miss Hoagie's class, I guess you're doing it on Monday. If you're in my class, we're doing it on Tuesday. Well, I guess Miss Hoagie's class, you have a Tuesday class as well. So yeah, thanks a lot for hanging out and going through some of these videos with me. I appreciate it. And we'll see you guys in class. All right. See you guys.